Hi, this lecture is about the impulse and change of momentum. So before we talk about what impulse is, let's review Newton's second law. So everything starts with Newton's second law here. So Newton's second law says force equals mass acceleration. I'm just going to say there's only one force, there's one mass, one acceleration, right? So let's express acceleration as the derivative of velocity over time. And now we can multiply the dt on both sides of the equation. So this whole thing multiplies by dt. Left and right sides are both multiplied by dt. So the left hand side is f dt, and the right hand side will not have the dt anymore. It will be just m dv. And if we assume m is a constant of the differentiation, we can put it back inside of the differentiation to make it dmv. The mv is momentum. So momentum is mv. So this equation looks like f dt equals dp. Okay, so now let's integrate both sides of the equation, and we'll integrate between time t1 and the t2. We'll have f dt equals dp. So this is also t1 to t2, or p-value p2, p1 to p2. And the right side integrates really easily into a p, right? And then you plug in p2, plug in p1, subtract the 2, that gets you p2 minus p1. And you can also say this is the change of momentum. Alright, so we have these two relationships. This one right here is a differential relationship. What it tells us is the change of momentum, a small change of momentum, differential amount of change, is caused by force applied for a duration, a very short duration. And if you integrate all that effect over a duration of time, that gives you a finite change of momentum. And that is due to a force applied for a duration of time between t2 and t1 and t2. So the force applied during a duration of time, the force may be a variable force in time, maybe a constant force of time, but the force being applied for duration causes momentum to change. And we call this change of momentum impulse. And in different textbooks, different symbols are used, sometimes capital I, sometimes capital J. So this is called impulse. So the impulse is simply the change of momentum. And how does that happen? Well, applying a force and for a duration of time, so momentum will change. Well, if you recall, there's a similar concept that's defined just like that. It's called work. Alright, work is W. So let's write backwards. Work is the change of kinetic energy, right? So K2 minus K1, that is equivalent to a delta K. And work is also defined as force dx, and we integrate from x1 to x2. I ignored the fact that these two can both be vectors, but even without vector nature, just say that there's a one-dimensional motion and a force pointing along that direction, so you'll still have a valid expression. So as you can see, here we have work, which is the change of kinetic energy. This is how much energy gets transferred. Well, energy gets transferred if you sustain a force for a distance. So the force has to be applied and the object has to move. And then this causes work to be done, energy to be transferred. And at the same time, if you keep this force for a duration of time, and even if the object may not move, you transfer momentum to the system. So this is a relationship between the impulse and the change of momentum. They're actually the same. So what caused the change? Force times the time, the duration. Okay, so let's take a look at an application. Say for example, we have a contact force, something that's say maybe a bat hitting a ball, right? Or maybe a passenger hitting an airbag. So what happens here is the force will not be a constant force. As the objects are hitting each other, they will deform and then they'll bounce off. So the force ramps up and comes down. So let's draw some diagram here. Let's say this is our time axis, this is our force axis. So an impact force could look like this. As time goes by, the impact starts and then it just dies off. All right. So okay. So the I can cut a small slice here. Okay, so here's a small slice. All right. So the small slice has a delta t and has an average force right here, F. So if you multiply delta t with F, that gets you, well, this area, right? And back here, delta t times F, that gives you the impulse or change of momentum. So the impulse of this entire collision will be equal to the whole area. So the impulse due to this small duration of collision, the contact is equal to this area. So this whole area is equal to the total impulse or total change of momentum. And a lot of times we may not have this exact knowledge of the force as a function of time unless we have some sort of a high-speed force gauge to sense the force, how it changes with time. This could be done with some sensors. But what we could also do is, if we start here, say this is T1, when contact is made between the two objects that are colliding. This is T2, when the contact is lost between the two objects. Okay, so if we have no knowledge of the shape, and that means we won't be able to find the area by slicing, right? We need to know the envelope in order to find the area. So let's assume that we know T1, we know T2, we know the whole big delta T, this whole duration, which could be still a relatively short value. And for some reason, we also know the total area because, see, the force times the duration is equal to change of momentum. So what do we already know? The change of momentum. So say we start from zero momentum and then we end up with some non-zero velocity, so we have a non-zero momentum. So we can calculate the difference between the two, and that could be done. So what we have here is, let's keep writing on the right side. So we have a force, some unknown force, right? And this duration to be integrated from T1 to T2, and we have P2 and we have P1. So let's just say this is equal to 0, start from rest, and this is equal to some known quantity. We know how fast it is after the collision, but we don't know how this force changes with time. So can we do something? Can we find some answers out? The answer is you can actually find an average force. So just imagine this whole thing, instead of a variable force times this dt, we can write this as an average force times the whole duration T2 minus T1, or this delta T. So equivalent diagram here, we start from here, T1, finish off T2, so it's roughly here, T2. So with an average force, let's say average force maybe here. So we're not exactly sure where this height is, but we know that this total area must be equal to this total area, and this average force will be a good estimate of the effect of this variable force, right? So although you don't really know the maximum force, you don't know the exact change of force, you have an average, so you can anticipate the effect of such an average force. So the way to calculate this is to use average force and times the duration of time, and equals P2 minus P1, assuming that you know both momentum before and after. So you can find an average force, which is equal to P2 minus P1 over the duration of the collision. Hopefully you can get that out, maybe with a high-speed camera, and then you can get a delta T. Okay. So what is the use of this? Well, we can quantitatively demonstrate this use. For example, let's say that there's a car and there's a passenger, and the passenger has a mass 70 kilograms, and the car is moving at a velocity 1 equal to 30 meters per second. This is close to about 66 miles per hour. And well, the driver slammed on the brake, so it took 3 seconds for the car to completely stop. Okay. All right. So say for example the seatbelt engages completely, so that restrains the passenger. And what is the average force the passenger feels from the seatbelt? Okay, we can calculate that using this formula. So we know that the passenger's momentum final, well, we know V2 is equal to 0 because the driver stopped the car, right? So the passenger will be stopped in the end, and the initial momentum is the mass times the initial velocity, right? So we can calculate how much force the seatbelt is acting on the passenger. This force here, average, is momentum 2, so that's mass times 0 speed stopped, minus momentum 1, mass times the initial speed, divided by a duration of 3 seconds. So a 0 minus 70 times 30, that's 2100 over 3. So that is 700 newtons of average force. So this won't be very comfortable, but it won't bruise the passenger either. So let's calculate with another situation where the passenger did not really wear a seatbelt, but there was an airbag, passenger airbag, deployed, and the passenger collided into the airbag. The car crashed, and the airbag was able to protect the passenger. The duration of the collision was, say, 0.3 seconds. It's a reasonable estimate. So let's continue on the right side. So now we say that delta T is equal to 0.3 seconds during a collision when the passenger only had the airbag. Okay, so we'll use the same formula. How much effective force does the passenger feel from the airbag? Okay, so the passenger still has to stop, so momentum 2 still is 0, and the passenger still has to start from the same exact velocity, but the duration of time is shorter, so 0.3 seconds. So this ends up being a negative 2100 over 0.3. So it's 10 times as big. So 7,000 newtons. If for some reason the passenger did not wear a seatbelt, the airbag deployed during a collision, and the airbag took 0.3 seconds. Basically, the passenger hit the airbag and took 0.3 seconds to stop. Okay, so let's assume that the passenger did not wear the seatbelt and the car did not have an airbag. The passenger may have hit the dashboard. It would be a very brief collision. So let's put it on the right side right here. Let's assume that this takes an order of magnitude shorter, 30 milliseconds. So very hard objects hitting each other is not unlikely to have a short duration of collision. So this value will still be the same, right? Still the same final state. The passenger stopped, and still the same initial state. The passenger was traveling at a certain speed. So the top is still minus 2100, but the bottom becomes 10 times faster. So now we end up with 70,000 newtons of contact force. So this is a very large amount of force. I can imagine bones breaking. So we were able to use an average force to make an estimate of something, a collision that happened if we have the initial velocity, the final velocity, and also we have knowledge of the mass and also the duration. We can make an estimate how much force, average force was involved, although this peak force is not known. Alright, so that was one thing we can do with this. Another thing we can do with this is, let's rewrite it. So force average equals momentum 2 minus momentum 1 over this duration. So momentum 2 minus 1 will be mass velocity 2 minus velocity 1 over duration. And I can also rewrite it as mass over the duration v2 minus v1. Okay, so what is this used for? Mass per t, that means how much mass is coming out of, say, maybe the end of a garden hose, water coming out of garden hose. How much water is coming out of garden hose per second? And how fast was it when it came out? And when it hits, say, maybe hits your car, you're trying to wash your car with a garden hose. And after that impact, well, on average, how fast is the water jet now? Maybe it's 0, maybe it bounces back quite a bit. So you'll have an estimate of final velocity here of the jet of water and initial velocity. Maybe you can assume that the final velocity is about 0 and initial velocity could be a few meters per second. And if you know how much water is coming out of your garden hose per second, you can calculate the effective force of a continuously pushing a stream of water, stream of particles, or a stream of anything, such as a stream of bullets hitting Superman's chest, right? So all of those can be estimated as an average force. This is not a single collision anymore, right? This is continuous collision that would effectively be equivalent to a force, a constant force applied to an object. And over here, what we did was a single collision, and the average force involved in that single collision can be estimated out of how fast before and after, and also the duration of the collision. Thank you.